Okay, in this video, we're going to talk about the fundamental theorem of calculus. The fundamental theorem says that if we have a function given by little f, and it's continuous on the closed interval a to b, and we have the capital F is the antiderivative on that interval, then this definite integral, the integral of f of x with respect to x from a to b, is going to be the antiderivative evaluated at b minus the antiderivative evaluated at a. So we basically just need to know the antiderivative, and we evaluate it at a and b and do the subtraction. Okay, so let's see how this works with a couple of examples. So let's evaluate the definite integral. So our little f of x, our integrand, is 1 minus 1 over x squared. So we want to come up with an antiderivative. So we can basically rewrite this as the integral from 1/2 to 2 of 1 minus, let's write this with the exponent, with a negative exponent. And we want to integrate this with respect to x. So the antiderivative of 1 is x, and the antiderivative of x to the negative 2, remember we add 1 to the exponent, and we divide by the result. So if we add 1 to negative 2, we'll get a negative 1. If we divide by a negative 1, that just cancels the negative in front. So we get plus x to the negative 1. And then what we do is we put this bar on the right side with our lower limit and our upper limit, and that tells us then we have to evaluate and subtract. So I'll have 2 plus 2 to the negative 1 minus, I'm going to put parentheses around this because I'm going to have to distribute the negative sign, 1/2 plus 1/2 to the negative 1. Okay, so this is 2 plus 1/2 minus 1/2 minus, now 1/2 to the negative 1 is 2. So I have 2 minus 2 and 1/2 minus 1, giving me an answer of 0. Okay, for this second problem, let's rewrite this. The integral from 0 to 4, I'm going to have a p, and then I'll put a 9 plus p squared to the negative 1/2. So we'll get rid of that radical sign, dp. Okay, so now in this case, I don't have an easy antiderivative. So what I will do is I will do this trick called u substitution. What I'm going to do is let u equal the part inside the parentheses here, 9 plus p squared. And then what I'm going to do is I'm going to take the derivative of u with respect to p, which is just going to be the derivative of 9 with respect to p is 0, and the derivative of p squared with respect to p is 2p. And then I'm going to say, well, this means that du is equal to 2p dp, and then I can solve this for dp and say that dp, that means that dp is equal to du over 2p. Okay, so now what I can do is I can substitute this all in. Actually, what I want to do first is I want to reevaluate my limits. So what I can say is that when p equals 0, the lower limit here, I'm integrating with respect to p. So when p equals 0, I get that u equals 9, right? I just substitute the 0 in here. U is 9 plus p squared. And when p equals 4, well, then I have 4 squared, 9 plus 4 squared, 9 plus 16. So u is 25. So what I will do is I will replace the limits of integration with 9 and 25. I'll have the p, I'm going to leave the p alone. I have a 9 plus p squared, but that's just u. So I'm going to replace that with the u. I have the negative 1/2. And the dp here, remember, is du over 2p. And now what happens then is the p's cancel. So that I have 9, the integral from 9 to 25 of u to the minus 1/2 du over 2. Okay, so now I can evaluate that. First, I'll pull the 2 out in front. So that's going to be 1/2, and then an antiderivative of u to the negative 1/2. I add 1 to the exponent, giving me a u to the 1/2, and I divide by that. So I have a u to the 1/2, and I have to divide by 1/2, which you see then these cancel out. And then I want to evaluate that between 9 and 25. So that means I take 25 to the 1/2 minus 9 to the 1/2, which is equal to 5 minus 3, or 2. And that's it.